Hello everyone, and welcome to Better Geotechnical Analysis and Design with LimitState GEO, which is the first LimitState GEO webinar for 2019. My name is Tom Pritchard. I'm the Principal Engineer here at LimitState, and I'll be introducing you to our speaker shortly and also doing a quick roundup at the end. Today's webinar will demonstrate a little about how LimitState GEO can be used to improve your workflow and also influence your geotechnical designs. You'll be able to discover a little about the technology behind the software and also see how it's applicable to a wide range of different situations. The main section of the webinar will run for about 35 to 40 minutes until approximately 1:40 UK time, and there'll be a few minutes at the end for questions, which you should be able to type in at any time using the question functionality that should be present in the interface in front of you. We will attempt to answer as many questions as we can, but given the short amount of time at the end, sometimes we can't always get round to all of them. We will, however, follow up on any unanswered questions after the webinar is finished. If you do have any follow-up in the days and weeks after the webinar, then you can always contact us via info@limitstate.com, and we'll be happy to answer all your questions in detail for you. So first off, I'd just like to introduce you to our speaker today, who is Dr. Colin Smith, and he's the LimitState GEO Product Manager.
Okay, thank you, Tom. So we'll get going straight away. So just to whet your appetite, we'll kick off with a slide showing a selection of problems types that can be solved by LimitState GEO. And we'll be discussing some of those later in the webinar. In terms of the contents, we'll be looking at the workflow with the software, how it can be used to conduct what-if type calculations, and then a quick look under the hood, how it works. So to this end, I'll primarily be using the software directly to illustrate the key points, but we'll make use of a few slides at the beginning and the end for introduction and summary. And as this is a short presentation, the main aim is to give you a flavour of what the software can do, and illustrate that using the software itself. So, next slide. So just a quick bit about LimitState. Our mission is to provide engineers with powerful software for ultimate limit state analysis and design, leveraging the state-of-the-art algorithms and latest optimization technology, and also to provide software that's robust and well-validated. Where we fit is the software fits between, on the one hand, sort of traditional a software that's based on traditional hand analysis solutions, and on the other hand, the nonlinear finite element type approach. And our software sits in the middle. So we get basically the benefits of the speed and simplicity of the traditional methods, but the flexibility to model any problem geometry that is given by the finite element approach. And in essence, all you need, because we're solving ultimate limit state problems, is cohesion, friction, and self-weight of the soil. So we'll just kick off by looking at one example of how you might approach a problem with LimitState GEO. And this is a retaining wall design example. So our problem specification is we have an embankment, for example, a road or a railway, and we need to widen that. So we're going to construct a stem wall, backfill that with granular material, and then this wide embankment needs to take additional loading. So the question is, how wide, for example, does the base of the foundation or the wall need to be, or how big does it be? What's the kind of stability? So if we look at that problem in a little more detail, or think about how we might analyze it, if we're going to use a traditional approach, a Rankine type analysis looking at earth pressures on the back of the wall, then we can postulate a virtual back behind our stem wall, but trying to think of different stress distributions is made slightly awkward because we have varied surface loads and we have this inclined soil interface. So standard Rankine formulae don't fit exactly in that case. Alternatively, we could use a Coulomb wedge. It's a little bit easier in terms of dealing with those issues, but is again fairly simple in that it doesn't capture all the possible failure modes. So we'll look at this, how we deal with this in LimitState GEO. So what we do initially is start with a DXF import of the initial design. So we can take that and work with that in terms of the geometry. So I'll just start up the software, and you'll see when I start software up, we've got a number of buttons on the top, menu bar, buttons down the left, mainly to do with the drawing of the problem, and on the top more to do with the analysis. We'll go through those as we proceed. So what I'll do is I'm going to do File, Import, Geometry, and it's already set up to pick up the right directory. So we've got a DXF file, and that produces an import window. We can move the geometry around, change the coordinates of the origin and so on, but I will just accept the defaults. And so that comes in like this with a number of construction lines. I'm going to just clear those, and that gives us the core geometry of the problem. Now, to actually undertake the analysis, we need to provide some material properties and some loads, etc. Sometimes you might not have the sign investigation data directly. You might just have a rough idea of what the materials are there. You can still do a kind of what-if type analysis just to get a feel for the problem. So what I'm going to do is look at the materials here. So that in the software of some preset materials, these are roughly approximate to the definitions of stiff clay, firm clay, etc., sand, and they can just be used for these kind of initial studies, but you can define your own properties at any point. So what I'm going to do very simply is take some material. You can drag and drop them onto the geometry, and I'm just going to populate this model like that. So I basically put very stiff clay on the bottom, stiff clay up here, and I'll use concrete here for the wall. So that gives me the materials. I'm just going to put a load here of 10 in this particular one. I'll make that a variable load. So these loads can be specified according to Eurocode type definitions. So I've got a variable load there, and then having got that, I could try running it. I get an error message which basically says no support is being supplied. So this is basically a block of soil floating in midair. So what I need to do is put some boundaries on, so I can select boundaries there, and can you print it out? Just another copy. So we'll set that to fixed, and the same for the bottom boundary. If I just zoom in, oops, set that to fixed. These buttons up here allow us to zoom in or go back to a full view, so I'll do that. You can zoom in or out on these using the mouse wheel, set those to fixed. So now we have the geometry set up, and if I click solve, the software rapidly gets to the failure mechanism and shows us how this system would collapse. So there's like a sort of foundation collapse for a wedge pushing sideways. So it's like a Coulomb wedge analysis, but with multiple wedges. And we get a solution of 42. So the question is, what does that mean? If you click on that, a little dialog pops up and explains what that means. So you recall we set a nominal value of 10 to the surface load up here. And what we're asked the software to do is assess, is that going to cause an ultimate limit state? And if not, what do we have to do to that load in order to get to an ultimate limit state? And so the software is saying, well, actually, you've got some quite strong soil here. In order to fail this wall, you're going to have to increase that value by a factor of 42. So that 10 has to be multiplied by 42 to get to 425. And that particular load will cause collapse in this situation. And that's one way of framing an ultimate limit state question. How much how much bigger does a load have to be to cause collapse. So that's a sort of introduction to how you might set the problem up and do some rough calculations. What we'll do now is have a look at the actual problem as was defined on the slide. So I'm just going to open up this pre-prepared problem. So what we have here is the setup as listed before. So this embankment material, anything I click on here, or here indeed, its properties appears on the right hand side. So this zone of material says it contains existing fill, and the existing fill has an angle of friction of 27 degrees and a unit weight of 18, which is what was defined on the PowerPoint slide. The granular fill that we're thinking of putting in here is somewhat stronger, so that's properties in there, and then we've got some basal materials here which have a stronger angle of friction. So that's all set up in that particular case. And we're going to analyze this using some Eurocode partial factors. So this can be set up with this feature here, Analysis Scenario Manager. And we've asked for Eurocode 7 Design Approach on Combination 2. So this will apply factors to unfavorable loads, and material properties as listed here. And all loadings you can define as favorable or unfavorable, as permanent, variable, or accidental. So the software knows how to factor those. So then we simply press solve, and we get a failure mechanism like this, and the result that we get is 0.77, and that is less than 1, which means that this does not comply with the Eurocode. So if we just click on that, see what it says. What it's saying is we've got these loads on the surface, 10, 45 and 10, and if I click on these you can see that the actual loads on the above are highlighted in purple. Because we've got Eurocode factors, and they're unfavorable variable loads, they're all multiplied by 1.3, and then on top of that we then have to multiply by this factor 0.77. So it's basically saying the Eurocode design values are too high, they will cause collapse, and they have to be factored down by multiplying them by 0.77 to get these values, which are pretty close to the starting characteristic values, in order for the system just to be on the point of collapse. So we have a situation where the current design is not going to work. So the question is, what can we do in that instance? So one option, if we look at the failure mode, is to see that what's happening, and we've got a slider bar here which allows us to animate the solution, that the soil is sliding down this interface between the existing fill and the newer, stronger fill. So it's using that weaker interface. So we could perhaps excavate more of the existing embankment as a possibility. So I've just put a vertex in there, and I'm just going to drag that back now that there's more space here, and I click solve. And that means that the failure mode looks the same, but now it's got to shear through the stronger new fill. And that's actually put our adequacy factor above 1.18. So that means that we have to increase those surface loads by 1.118 to get failure. So that means that would comply with the Eurocode. So that's one option, but that means excavating material. So we'll just revert that, and I've buttons here that allow me to undo changes that I've put in. So again, if we look at the failure, what happens is this wall is sliding, but it's also causing the material below the wall to fail. So perhaps we could make that somewhat stronger. So if we replace that with the stronger basal material, for example, so our granular fill has an angle of friction of 34, basal deposits angle of 40. So if I can just simply drag and drop and put that in there, and I get a new material. I also have to be careful of the interface material. So in this particular example, we've introduced a material on the interface between the base of the wall and the underlying soil. And that material was originally set to have 3/4 of the strength, these are multipliers, on a parent material, which was the granular fill, which is what was originally underneath this wall. We need to change that now, and I'm going to change it to this material, which we've pre-set. That's called basal deposits wall interface. Again, we've got this multiplier 3/4, but that's applied to the new parent material, which is the basal deposit. So that means that this interface is modelled as having 3/4 of strength of the soil underneath. So again, I need to take that material, drag and drop it onto that interface, and we've got that all set up. And then I can just solve the problem again. And this time the stronger fill doesn't fail under the wall. The wall basically just slides, and we get an improved adequacy factor, which again is above 1, and therefore that means that the system complies with the Eurocode. That, of course, again means excavating material, replacing it, so or bringing in stronger fill. So if I undo those two changes, one other thing we can look at is perhaps suppressing the failure under there by increasing the surcharge on this side. So what I've got here is a kind of truncated block of soil there, which I'm just going to push up. And if we put a bit more weight there, that will hopefully suppress that mechanism. So again, we look at that, and that's done the trick. This is now sliding rather than causing a bearing failure. And again, we've brought that factor up above 1. So very quickly, we've explored a number of options that we might wish to adopt in order to get this design to work, and then we can explore those in more detail and scope them out as to in detail. Before we leave this example, just to show you the report that you can generate with the software. So if I go analysis report, after any solution, I can generate report. I'm just going to accept all those defaults, and you get a report. This is in an RTF format, so you can import that into something like Microsoft Word. It gives you all the results, this adequacy factor there, drawing of the failure mode, if you want it, all the geometry, boundary conditions set, the material properties used in the problem, partial factors. And again, if you want, for simple mechanisms, you can actually get free body diagrams of the entire mechanism if you wanted to interrogate that in more detail. So that's the reporting out of that system. And what I'll do just to wrap this particular case up is say, for example, what would happen if this site flooded and the water table rose. So I've got a water table here. I'll just draw that in to this position. And I need to, just need to enable that water. We've disabled the water here, so I'm just going to enable that. So we now have a water table there sitting just slightly above the ground level, and if I solve that, we get a new analysis and the adequacy factors drop below 1. So as we expect, the presence of water is going to make the system weaker, and that now does not comply with the Eurocode. So again, you can look at scenarios where with adverse water conditions and see whether that's going to change the stability. Okay, so that's a quick look at exploring a problem there and the kind of workflow that you might have with the software. So I'm just going to shut that down and go back to our PowerPoint presentation and do a kind of what-if type analysis, this time looking at a simple slope stability problem. So we're going to look at a slope here that if you do it by a method of slices solution, Bishop's method, you get a factor of strength of 1.6 on this. That type of analysis was originally designed for hand calculation and requires an assumption of interslice forces and often requires specification of zones or entry-exit points and centers of rotation. With this software, you don't need to enter any of that. It will search for the most critical collapse mechanism, and you don't need any of these assumptions of interslice forces. Typically, we assess slopes as a factor on strength. In our previous example, we were looking at how much bigger we'd have to make a load to cause collapse. Here, what we're interested in is what strength, a factor on the strength of the material would be required to cause this system to collapse, and we can get the software to do that quite easily. So, yeah, just go back to the software. Let's cancel that, and I'm just going to open this example. Footing one. Oops, no, sorry. Pick the wrong one there. I meant the drain slope. Okay, so that's the example that we saw on the slide. We are using what's called factor strength mode here. We've got a choice of factor load, which is what we're using in the previous example. Factor strength here tells us what factor on the strength is required to cause collapse. And this soil is basically soil here, A here, which is a C-5 at 530. So click solve. Software determines that we have a fairly shallow slide, similar to the one in the PowerPoint, and here we get a factor on strength of 1.63, so that's very close to that 1.6 from the method of slices, and generally the method of slices for these simple type of slope problems will give very similar results. If I click on the solution here, again it brings up the dialog, and you can see this time the results reported in terms of the effect on the soil. So we've got the properties of our soil A, C-5, phi-30 with the original characteristic values. In this example, I haven't put any Eurocode factoring, so the design value is the same as the characteristic value. And what the software is telling us is that you've got to divide these values by 1.63 to get these values, and at those values, the slope will collapse. So essentially, we have a factor of safety on strength of 1.6 in this case. Now we can explore the effect of changing the conditions here. So again, perhaps we might have what if someone dumps some material at the top of the slope, or parks a vehicle there. So I could put a load up on the surface. And I'm going to add a variable load of 5, normal load. And that's unfavourable. And I can solve that problem again. And we get a factor of 1.62, so it really hasn't made a great difference. Most of the stability of this slope is controlled by the weight of the soil itself, and that relatively small surcharge has not made a major difference to the analysis. Alternatively, sometimes with slope problems there are pre-existing failures, so we can model one of those. I'll do that fairly simply. If I draw a line here, there to there, so there I was using this line drawing tool on the left, and I can impose a different material on that, just like we did with the interface between the base of that stem wall and the soil. So what I'm going to do here is make that interface soft clay. I'm just putting a weak material in there. It may not be terribly realistic. And that interface now has that property. I can also change the shape of the interface by adding vertices. So if I wanted to give it a slightly more curved shape, I can add vertices on there and change the geometry. Any geometry that I click on here, the coordinates appear here. You can also type in coordinates rather than dragging with the mouse. You can use construction lines, or you can obviously import from the DXF file. So we've got this scenario here. If I click solve, we get a different failure mechanism this time. So this time the weakest failure is to slide down quite a long length of that weaker interface, and we get a significantly reduced factor on strength of 1.166, whereas before it was 1.6. So we can play around with the geometry here, we can play around with loading, do sort of what if type calculations. So if we had a suspicion there was a pre-existing slip surface and a rough idea what that strength would be, we could say, well, what if it was there, what would it give us? I'm going to move on now to have a little more detailed look at Eurocode partial factor sets. So we're going to look at some footing problems. So let's pick this one, simple footing one. So what we have here is a very simple footing sat on the surface of a soil. This soil has properties, footing soil, undrained strength of 70 or a drain strength of 0 and 30. So in the software you're able to enter both drained and undrained properties, and then you can use an external switch to swap between them. So that means you don't have to set up two sets of models. If you want to do a drained analysis and undrained analysis, you can simply set one set of properties and then switch between them. And this is set by this global setting here, long-term analysis. So if it's true, it will use drained parameters. If it's false, it will use undrained parameters. So in this case, we're going to be using those undrained parameters for this material, a CU of 70. We have here on the surface of the load here, we have a permanent load of 1/2. Now the footing has a length of 2, so its coordinates run from a -1x to +1x, so it's got a width of 2. We're applying a normal stress of 1/2, so that means we're actually applying a unit line load to this footing by setting that to 1/2. And we're in factor load mode up here, and if we set this flag here, adequacy to true, what we're telling the software is what do I have to multiply that load by to cause collapse. So by putting in a unit load there, what effectively I'm getting the software to do is tell me what is the bearing capacity of this system. In contrast, I've got these other loads here, and these are displayed by green arrows, and these are basically just surcharge loads. Again, they're permanent, surcharge of 10, but they have an adequacy of false, so they're just treated as constant loads. The software is not being asked to multiply them and find out what value is required for collapse. And finally, we'll look at scenarios. So here, what I've asked the software to do is model multiple scenarios. So for every solve, it's going to solve the problem with no factors applied, unit factors, with design approach 1 combination 1 factors applied, and with design approach 1 combination 2 factors applied. And then we can look and see which is the most critical case. So if I click solve, quickly it runs through all 3 analyses, and I get different adequacy factors, and the most critical case is design approach 1 combination 2, and it's telling me that I can apply a load of 502 kilonewtons to this, or kilonewtons per meter to this foundation before I get collapse. If I click on the result, again you can see that the load on interface B1, it's a characteristic value of 1/2, design value of 1/2, and I need to multiply by 500 to get this collapse value. Remember, that's a stress, and we're multiplying it by 2 to give me that line load. So that illustrates how we can use the software to effectively quickly run through a number of different partial factor sets, particularly useful for design approach 1 in the Eurocode. Just quickly show you one other example. What I'm going to do is open my second footing problem, that one there. So this is slightly different here. We've embedded the footing a little bit into the soil. We've got we've got these interface materials around the edge, and these are actually set to have the same strength as the parent material, but we could change those values if we wished. Again, we have this a variable load this time, but again, a value of 1/2 spread over a width of 2. So we've got a unit line load effectively applied, and then we have a surcharge at the sides of permanent surcharge of 10 kPa. Now in this particular problem, the soil itself has this undrained strength of 70, but we're able to give it a linear gain in strength of depth. So these two parameters here allow us to give us, in this case, a nice round number of 1 kPa per meter depth gain in strength. And I can view that by a preview strength here, short-term strength, the undrained strength, plots me a graph of how the strengths change, and as I move down I can see that strength building up. So it's not a huge gain in strength of depth in this particular example, but I can change the value to whatever I like. So if I click solve on that, I get a different mechanism. I get again the same 3 analyses again. Design approach 1 combination 2 is critical, and I get 518 as the collapse load. And again, if I click on that, you can see that that variable load did have a value of 0.5. Because it's now variable, that load that I've applied to surface, the Eurocode, the most critical case, design approach 1 combination 2 applies a factor of 1.3 to it, and then on top of that I've got to apply this factor of 518 to get to the collapse value. We can also analyse scenarios where we have, for example, lateral loading. So I can add it's the variable load, lateral load of 0.2. So now we have effectively an inclined load on that, and if I solve that, I get a different failure mechanism, a different adequacy factor, and again you can see the application of the partial factor and that overall factor on the system. So it's very easy to change the loading patterns, the soil properties, and explore different failure mechanisms and different geometries. So hopefully that's given you a flavour of some of the features of the software. Ease of change of materials, properties, loadings, geometry, also application of partial factors, and how we interpret the results from the software. What I'm going to do is wrap up, just close that file and wrap up just by explaining how the software works. So it's built on a technology called discontinuity layout optimization, which is a rapid and direct means of analysing the collapse state. Came out of a 5-year EBSERC research project carried out at the University of Sheffield, published in the Proceedings of the Royal Society in 2007. It's relatively easy to explain how it works. So here's a very simple scenario. We have a rectangular block of soil supported on its base on its left-hand side, and we have a surface load. Instead of discretizing the domain into elements, which you do in a finite element approach, this uses a node-based approach. So here we put nodes across the domain, in this case a 4x3 array of 12. And what we do is, in essence, we connect every node to every other node with a potential slip line. And then we use optimization techniques, very powerful optimizers that can deal with many, many variables, to look at all those possible slip lines and pick out the key set that cause failure. So here we've got 12 nodes, so we've got 12 times 11 over 2, 66 connections. Out of that, the critical set are these 6 slip lines, and that gives the most critical collapse mechanism, or the one that essentially dissipates the least energy. So it's essentially an optimization problem looking for the minimization of energy dissipation. This is a very simple problem with just 12 nodes. The examples I was showing earlier, we use 500 nodes, and you can quite easily solve with 1,000, 2,000 or so nodes. And generally you get answers very rapidly, as we've seen, and to a high degree of accuracy. And essentially the message is the more nodes you put in, the more freedom the software has got to pick a collapse mechanism as close to the one that would actually happen. So in this particular example, you can see all the nodes in this animation. We'll let it run through again, but those nodes in the background, and the software is basically exploring all those possible slipline connections, finds the critical mechanism, and then animates it to aid interpretation. That animation is strictly only valid instantaneously at the point of collapse, but we extend that to make it easy to follow, but you get some kind of anomalies like appearing down there. The software is extensively tested. Every time the software is altered, it runs hundreds and hundreds of tests to make sure that it is doing the right thing. Many of these are available on the website, and you can look at those and see the results. So here's one example of the classic sort of Prandtl punch or footing on a clay soil, and it gets to within 1% of the exact solution in less than a second. One of the nice things about this particular method over finite elements is that it deals with what are called mathematical singularities in the solution without difficulty. So effectively, where you get a fan zone of sliding elements, which are quite common in ultimate limit state problems, this can be quite difficult to deal with in finite elements requiring mesh refinement and so on. This method deals with this inherently. No extra programming or measures need to be taken. So as I said, it's been verified against a wide range of solutions and benchmarks, and these can be looked at on the website. You can download the files, test them out yourself, and that covers a whole range from anchors, trapdoors, retaining walls, foundations, etc. There's also quite an extensive bibliography now of academic papers using this software or showing how the method can be developed further. And again, you can download this from our website, and there are over 50 papers on this list, covering a whole range of examples, again, foundations, slopes, retaining walls, etc. I'm just going to wrap up the presentation, just showing you a few more examples of how the software can be used to solve a wide range of problems, and the software has built-in wizards that allow you to set up some of these problem types very quickly. So I haven't had time to show you all the features, but hopefully these slides give you a flavour of some of those problem types that can be solved. So as we're coming towards the end of this webinar, just wrap up with a few conclusions. So I hope you've seen that the workflow using the software is straightforward, from geometry import to reporting. So it's a very intuitive user interface, so you're in control of the problem. You can solve with one mouse click. It's very easy to apply partial factors. Very easy to solve those kind of what-if type questions. What if the soil isn't quite as strong as it is, or the geometry is slightly different, or if I put a different material here, and allows you to get a much better feel for the problem very quickly to come to the decision as to what to do in the end in terms of your design or assessment. And hopefully you've seen this one piece of software can solve any ultimate limit state problem type. So you don't need to put in idealizations or correction factors for non-standard geometries, or impose assumptions as you do with some slope analyses. And you don't need to learn how to use many different programs. You can solve this whole range of problems as we've seen with the one piece of software. So at that point, I wrap up the webinar. We've got about 5 minutes left for questions. So you can type those questions in via the webinar interface, and I'll just answer as many of them as I can in the last time that we have. Okay, so question: can I model earthquake loading? So the answer is yes. The software is set up to model earthquake loading using pseudo-static approach. So, for example, I can look at a slope stability problem. I'm just running standard wizard. These wizards take you through just setting up a simple geometry. I'm just going to leave this as defaults. Skip through all of that, and that gives me a very steep slope here. Now this is currently modeled as a clay slope. If I do a factor strength analysis, it tells me that I would get collapse in this way, but I have to reduce the strength on the soil by a factor of 2.5 to get failure. I can apply seismic actions here. So again, this property editor on the right, the global system properties are displayed by default unless I click on some specific item. But if I click anywhere on the empty space here, I get those. And there's an entry here for seismic actions. So I can apply horizontal and vertical accelerations. Let's click on that. Now anything you click on here, a little description appears down here. So it says specify a positive value for a left to right base acceleration, i.e. likely to lead to right to left soil movements. So if I want the slope to fail from right to left in the way that it was before, I need to put a positive value in here. So if I put in a, say, horizontal acceleration of 0.3, now I can choose to have adequacy on that, so I can choose for the software to tell me how much bigger does that have to be to cause collapse. But because I'm on factor strength mode, I'm going to leave that fixed and then solve. And what we should hopefully find is that we get a somewhat different failure mechanism, and the factor of strength has gone down, and that's because we got that effectively horizontal seismic loading on the slope, wanting to drive it to collapse, and therefore we have a smaller margin of safety on the system. And while we've got this up here, one thing you can see is that this line intersects the top of the boundary. Now this boundary is in essence artificial, and so unless it actually represents a wall of rock or something, it's actually too far out and it's affecting the result. So if we see that, we ought to move it back. I'm just going to do that quite crudely by dragging and dropping the geometry. And then if I solve again, I find the mechanism wants to fill that gap, and actually this is a case where no matter how far out you move the boundaries out, the mechanism will always grow, because in theory the critical mechanism has an infinite scope. So I'm onto a kind of losing wicket in this particular case. But if we assume there is bedrock down here, if I do move that out further, then let's zoom in on that. Oops. So I should eventually get to the point. It still wants to be quite large. It's because we've got quite a high acceleration on the system, so that mechanism will move back quite significantly. So the answer is yes, you can model pseudostatic accelerations, and you can ask a software either how big does the accelerations have to be to cause collapse, or if I apply a fixed acceleration, what is the factor of safety on, for example, strength. Another question is, can I model geotextiles? So let me just go back to our original geometry there with no acceleration. So the answer is you can model reinforcement in the soil, and the way you do that is effectively you put in layers of reinforcements. If I draw a boundary line here, and I'm just going to put a vertex in here, I've got a length of boundary, and I can actually assign a material here we've called a geotextile. I haven't got time to go through the properties of that, but effectively it models a one-dimensional material that can transmit tension along its length. So effectively it's representing a geotextile, and it uses exactly the same mechanics, underlying mechanics, as in most classic analyses of reinforced earth problems. So having put that in there, I click solve. Hopefully that will change the mechanism. So we've got a slightly different failure mechanism than when I didn't have it, and actually what the software has said is because you've got that in place, it's taking a failure mode outside the geotextile, but I should be able to force the failure mechanism to go through the geotextile just by making it longer. Yeah, now there's a failure surface cutting through the geotextile. And I get a changed factor on strength of the system. And the software also plot out, in this case, it's displaying the tensile force in that geotextile along its length as those stresses are transmitted from the soil into the geotextile. So the answer is yes, it can. I can't really show the full capability in this very short period, but that's one illustration. And you can also use this one-dimensional element to model, for example, a sheet pile wall. And there is actually a wizard that allows you to model that. That's this one here. Just click Finish. And we're modeling a rigid one-dimensional element here. We've got clay behind the wall. And we can look at the failure of that again in terms of factor of load or factor on strength. In this particular case, you can see, because we've got clay behind the wall, it's actually the software is correctly modelling a tension crack opening up in that particular case. Just checking through questions. Okay, so apologies, I'm running slightly over. I'll pick up one last question, then we'll have to finish there. So one question is, how does the software actually determine which failure surface is the critical one? So effectively, you can think of it as looking through all the possible failure mechanisms that are made up of all those possible failure slip lines. So if we go back to the PowerPoint presentation. So it's basically looking through millions and millions of possible combinations of slip lines and picking out the ones that give you the critical failure mechanism. It's doing that using very powerful linear optimizers, which are guaranteed to find the global optimum rather than local optimum. So it will always find the most critical mechanism out of the set of initial slip lines that you allow it to use, and that's defined by how many nodes you tell the program to use. And it's very easy to change that number through the interface on that. So effectively, that's how it is. It's just using linear optimization technologies that currently can deal with millions of variables very quickly on modern PCs. So they're very powerful and will always give you that critical or the minimum energy collapse mechanism. So that's effectively how it's finding where the critical case is. Okay, in view of the time, I think I do need to wrap up there. So thank you very much for your attention. Hope you found that useful. I will just pass back to my colleague Tom to wrap up the session. Thank you.
Thanks, Colin, and thanks to everybody who's joined us today. We do hope you found the webinar informative. And for those of you who aren't current users of LimitState GEO, we will try and get in touch over the next few days, just find out if you have any further questions about the presentation or the software. As mentioned, if anybody has any follow-up questions, then please do email us on info@limitstate.com and we'll get back to you as soon as possible. You may also be interested to know that we have a number of different webinars coming up over the year which cover all of the LimitState product range, and some of them which will focus more on particular problem types and applications. So please do look out for those notifications which we'll send out closer to the time. They'll be on our website, on our social media, and also email if you're signed up to our email list. So lastly, just like to thank you all again for taking the time to join us today, and we do hope to see you all again for one of the future sessions. Goodbye.